Welcome back to QHSE Talks.
Hey, glad to be back. We have a heavy one today.
We really do, literally and figuratively. So imagine a worker walks into your office.
Okay.
There's no broken bone poking through the skin. There's no blood on the floor.
Right, nothing obvious.
Exactly. There's no jagged white line on an x-ray that you can just point to. They just, rub their lower back, look you right in the eye and say, that new pallet in shipping is too heavy.
Oh, yeah. The classic vague complaint.
Right. So as a safety professional, how do you prove it? I mean, how do you take a vague, highly subjective complaint and turn it into undeniable, hard mathematics?
Because if you just go to management and say, well, the worker feels like it's heavy, you're not going to get the budget for a new crane or a lift table.
You won't get a single dime. Management operates on data.
Exactly. Engineering operates on data. And the human body, for all its immense complexity, it operates on the laws of physics.
Yeah, gravity doesn't care about feelings.
It doesn't. So the challenge for the occupational health and safety professional is bridging that gap. We have to bridge the gap between a worker's subjective discomfort and the objective reality of biomechanical stress.
We basically have to quantify the invisible forces acting on the spine.
Precisely. We have to make the invisible visible through math.
And that is the exact hurdle we are tackling today. I am talking directly to you, the safety professional listening right now.
Yep. The one studying for the exam.
Exactly. Maybe you're commuting to your site, or, maybe you're sitting at your desk with your flashcards spread out everywhere, or maybe you're just trying to conquer those math-heavy portions of your certification prep.
And we really know those math sections can be a major source of anxiety.
Oh, absolutely.
If you look at the examination blueprint for the Associate Safety Professional exam, the ASP 11 blueprint, Domain 1, is completely dedicated to advanced sciences and math.
It's a huge chunk, isn't it?
It is. Mathematical calculations make up a full 10% of the exam blueprint. That is a massive chunk of your final score. Honestly, it's often the difference between a pass and a fail.
Right. So our mission today is laser focused on conquering one of the biggest beasts in that entire domain. We are doing a QHSE Talks specifically on ASP 11, Domain 1, Topic 9.
Which is calculate manual lift parameters.
Exactly. To be super specific, we are going to completely master the NIOSH Lifting Equation.
Yep.
We aren't just going to memorize it, right? We are going to understand the anatomy, the history, and the exam strategies behind it.
Because memorizing without understanding is how you fail the tricky questions.
Totally. Okay, let's unpack this. Before we even look at a formula, where did the standard actually come from?
Well, we have to look back a bit.
Because, 100 years ago, workplace safety was basically just, hey, if you can pick it up, it's your job.
That's entirely accurate. Historically, the approach to manual material handling was incredibly rudimentary. It was essentially based on brute force and trial and error.
Wow, trial and error with human spines.
Yeah, not great. The International Labor Organization, for instance, used to have past recommendations that were largely arbitrary.
Like what?
Well, they suggested a maximum permissible weight of 55 kilograms for adult male workers.
Wait, 55 kilos? That's about, 121 pounds?
Yep, 121 pounds.
121 pounds is a standard baseline. That seems outrageously high for a repetitive task.
It was dangerously high. And their recommendation for women was even less scientific, if you can believe that.
Oh boy, what was it?
It simply stated substantially less than permitted for males.
You're kidding.
I wish I was. There was zero biomechanical rigor to it. It was just a blanket weight limit that completely ignored how the lift was actually being performed.
So it assumed lifting a compact 50-pound iron weight off a waist-high table was the exact same physical event as, say, lifting a 50-pound floppy bag of flour off the floor while twisting your spine.
Exactly. And the body does not experience those two events the same way at all.
Which makes sense. I can curl a 30-pound dumbbell, sure, but if you ask me to hold a 30-pound television straight out at arm's length, I'm going to drop it in 5 seconds.
Right, because of leverage. So the shift really happened when occupational epidemiology started catching up. By the late 1970s and early 1980s, musculoskeletal disorders, specifically lower back pain, were becoming the most expensive and prevalent occupational health issue in the world.
Just a massive financial drain.
Massive. Workers' compensation costs were skyrocketing. So the National Institute for Occupational Safety and Health, NIOSH, finally stepped in. They published their first lifting guidelines in 1981.
Right, but the version we use today, like the one on the ASP exam, that's the revised version from 1991, right?
That is correct.
What changed in that decade?
Well, the 1981 version was a good start, but it was limited. It primarily looked at just the sheer weight and the geometry of the lift. By 1991, NIOSH realized they needed a holistic model.
A more complete picture.
Yes. So they released the application manual for the revised NIOSH Lifting Equation. This revision brought in 3 distinct scientific disciplines.
Okay, what were they?
First, biomechanical data, which looks at the spine as a mechanical lever system. Second, physiological data.
Which is like, what, heart rate?
Exactly. It looks at the metabolic cost, so how fast your heart is beating and how much oxygen you are consuming. And third, psychophysical data.
Psychophysical, that's a big word.
It is. It's essentially research on what workers perceive they can lift safely over time.
Oh, I see. So it's the combination of the machine, the engine, and the driver's perception.
That's a great way to put it. And the ultimate goal of combining all this data is to produce a single actionable number, the recommended weight limit, or the RWL.
Let's define that really clearly for everyone listening. What exactly does the RWL represent in the real world?
The RWL is a very specific, carefully calculated threshold. It represents the weight of a load that nearly all healthy workers could lift over a substantial period of time without an increased risk of developing lower back pain or injury.
Wait, let me stop you there and clarify something that usually trips people up on the definitions. When you say nearly all healthy workers, the source material actually assigns a statistical percentage to that demographic, doesn't it?
It does, yes.
Because it's not literally 100% of the human race.
No, definitely not. The NIOSH guidelines define nearly all as 75% of the female population and 99% of the male population.
Okay, got it.
When you average those demographics out, the equation is designed to protect roughly 75% of the healthy general working population.
And a substantial period is defined as an 8-hour shift, right?
Yes, exactly an 8-hour shift.
So if we calculate a job task and find the RWL is 35 pounds, we can basically tell management with statistical confidence that the vast majority of our workforce can perform this task all day, every day, without destroying their lower backs.
That is the power of the equation. It provides a defensible, objective standard. And to start that calculation, the equation doesn't just leave you guessing. It gives you an absolute baseline to begin with.
Right, the golden baseline.
Yes, it's called the load constant, or LC. For the revised NIOSH lifting equation, the load constant is set in stone at 51 pounds.
Or 23 kilograms if you were working in a metric region.
Exactly.
You know, I've always conceptualized the load constant of 51 pounds like getting a 100% perfect score on a test.
I like that analogy.
Yeah, imagine an absolutely perfect, frictionless laboratory environment. You are standing in the perfect neutral posture. The box has incredible handles. It's right at your belly button height. You don't have to twist your body at all. And you only have to lift it one time.
The absolute ideal scenario.
Right. Under those flawlessly ideal conditions, the maximum baseline weight you can safely lift is 51 pounds. Every other variable in the real world is going to act as a deduction from that perfect score.
The structure of the equation itself proves that concept perfectly. The formula you will see on the ASP exam is this: RWL equals LC, multiplied by HM, VM, DM, AM, FM, and CM.
That is a lot of letters.
It is. But it's just the load constant of 51 multiplied by 6 different variables. And the mathematical key here, the most important part, is that every single one of those 6 multipliers is a fraction.
Meaning they're decimal values representing a percentage?
Right.
They can only ever be a number between 0 and 1.0.
That concept is absolutely vital for the exam. Because you are multiplying the baseline of 51 pounds by fractions, the recommended weight limit can only go down. It can never, ever go up.
So you can never achieve an RWL of 60 pounds.
Impossible. 51 is the absolute biomechanical ceiling. If a task requires a worker to adopt a terrible, awkward posture, the multiplier for that posture might be, say, 0.5.
Okay.
You multiply 51 by 0.5, and you have instantly slashed your safe lifting weight in half.
So you're down to 25.5 pounds.
Just like that.
Wow. Okay, so we figured out the penalty for a less than perfect scenario, but nobody gets paid to just stand there in a lab. Real work happens in three-dimensional space. We need to figure out exactly where the worker's hands are in relation to their body when they make the lift. So let's dive into the first 2 variables, the spatial multipliers.
Sounds good.
I want to start with the horizontal multiplier, the HM, because from what I see in the source material, this one carries the harshest penalties.
It really does. The horizontal multiplier evaluates how far the load is held away from the body. To understand why this is penalized so heavily, we need a really quick anatomy lesson.
I'm ready.
The human spine acts as a lever, and the fulcrum of that lever is the L5-S1 disc.
Okay.
That is the disc located at the very bottom of your lumbar spine, right where it meets the sacrum.
So basically right at the belt line.
Yes, right at the belt line. When you hold a weight in your hands, gravity pulls down on the weight, creating a moment of force that tries to pivot your entire upper body forward around that L5-S1 fulcrum.
Ah, I see.
To stop you from falling over face first, the massive muscles in your lower back, the erector spinae, have to contract and pull backward with incredible force.
It's like a seesaw. If the box is on one end of the seesaw, your back muscles are on the other end, pulling down to keep it level.
That's exactly it. The problem is leverage. The back muscles are positioned very close to the fulcrum, just a couple of inches away. But the box in your hands might be 15 or 20 inches away.
Right.
Archimedes said, "Give me a lever long enough, and I shall move the world." In this case, the longer the horizontal distance, the more leverage the box has against your spine.
Oh man, that's not good.
No, to balance a 50-pound box held far away, your back muscles might actually have to exert 500 pounds or more of internal force.
500 pounds.
Easily. And all of that force compresses the L5-S1 disc. That severe compressive force is exactly what blows out discs and destroys careers.
That paints a terrifying picture, honestly. So how do we quantify that horizontal distance? What is the actual metric we use?
We use the variable h. H is the horizontal distance measured in inches from the midpoint between the worker's inner ankle bones to a point projected straight down from the hands grasping the object.
Okay, wait, let me make sure I'm picturing this right. Why measure from the ankles? Why not just measure from the chest or the belly button out to the hands?
That's a great question. We measure from the ankles because they represent the body's base of support and center of gravity when standing.
Right, because your feet are on the floor.
Exactly.
Yeah.
The chest or stomach can move independently of the center of gravity if the worker leans forward or hunches over. The ankles provide a fixed, stable reference point for the whole biomechanical system.
Got it. So the formula for the horizontal multiplier is fairly simple, actually. It's HM equals 10 divided by H.
Yep, 10 over H.
Let's talk about the limits of this formula. The source material states that the absolute minimum value for H is 10 inches. If a worker is holding it closer than 10 inches, you still just use 10 in the math. Why is there a minimum?
It just comes down to physical reality.
Like body mass.
Right. The average human body has thickness. You cannot hold the center of mass of a standard box any closer to your ankles than 10 inches without the box physically phasing through your torso and your thighs.
True, unless you're a ghost.
Exactly. So 10 inches represents holding the object completely flush against your stomach. If H is 10 inches, the equation becomes 10 divided by 10, which gives you a perfect multiplier of 1.0.
So you face zero biomechanical penalty because the load is as close to the fulcrum as physically possible.
Correct.
But let's say they have a workstation where, I don't know, a conveyor belt is blocked by a guardrail, and they have to reach their arms straight out across a table to grab a tote. Let's say H becomes 20 inches.
If the horizontal distance is 20 inches, the math is unforgiving. 10 divided by 20 is 0.5.
Wow.
By simply reaching your arms out 20 inches away from your body, you have immediately destroyed 50% of your safe lifting capacity.
So your 51-pound limit is now a 25.5-pound limit.
Just from reaching out.
That penalty scales so aggressively. And there's an upper limit too, right? What happens if they have to reach even further?
The maximum allowed horizontal distance in the NIOSH equation is 25 inches. 25 inches is roughly the maximum reach distance for an average person without completely losing their balance or falling over.
So what happens to the math if the distance is, say, 26 inches?
If a worker has to reach further than 25 inches, the horizontal multiplier immediately becomes 0.
Just 0.
0. And because it is a multiplier in a string of fractions, multiplying the entire equation by 0 means the final recommended weight limit becomes 0.
Wow.
The equation is explicitly telling you that the lift is fundamentally unsafe and should not be performed manually under any circumstances.
This is a massive strategy point for the ASP exam, isn't it?
Huge.
If you are taking the test and you read a long paragraph about a scenario and you spot that the horizontal reach, the H value, is 28 inches.
You stop reading.
Right. You don't need to calculate the vertical height. You don't need to look at the grip or the frequency. The multiplier is 0, so the RWL is 0. Do not waste 5 minutes on your calculator. Pick 0, save your time, and move to the next question.
Absolutely. The test writers will deliberately give you a full page of data for a lift with a 30-inch reach just to see if you will waste your time doing the math.
That's so sneaky.
Knowing the limits of the variables is just as important as knowing the formulas.
All right, that thoroughly covers the horizontal plane. Let's look at the vertical plane, the vertical multiplier, or VM. We know how far away the box is. Now we need to know how high off the floor it is.
Right. The vertical multiplier evaluates the location of the hands vertically relative to the floor. The variable here is V, which is simply the vertical height of the hands above the floor measured in inches.
Now, I have to admit, when I first looked at the formula for the vertical multiplier, it looked like, well, audio math designed to confuse people.
It does look intimidating at first.
It's VM equals 1 minus 0.00075 times the absolute value of V minus 30. And just like H, V has limits. It has to be between 0 inches, which is the floor, and 70 inches, which is the maximum vertical reach.
Exactly.
But before we crunch those numbers, you have to explain the concept to me. Think of it as a penalty tax. What is the baseline we are starting from, and why is the number 30 hard-coded into the formula?
What's fascinating here is that the concept is built around what ergonomists refer to as the strike zone.
Like in baseball.
Very similar. If you take an average worker and have them stand perfectly straight with their arms hanging naturally and comfortably at their sides, their knuckles will be roughly 30 inches off the floor.
Oh, okay.
At this exact height, the spine is in its most neutral alignment, the shoulders aren't engaged, and the body doesn't have to fight gravity to maintain the posture. It is the point of maximum biomechanical efficiency.
So 30 inches is the sweet spot. It's basically the gold standard height for a workbench.
Precisely. Let's look at how the math proves that. If V is 30 inches, we plug that into the absolute value brackets. 30 minus 30 is 0.
Right.
Multiply 0 by the penalty coefficient of 0.00075, and you still have 0. Subtract 0 from 1, and your vertical multiplier is 1.0. You pay 0 penalty tax.
But the moment you deviate from 30 inches, the moment you move away from your belly button area, the absolute value brackets kick in. Why use an absolute value, though? Why not just a standard subtraction?
The absolute value is the mathematical way of ensuring you are penalized equally, regardless of direction.
Meaning up or down.
Yes. The equation doesn't care if you deviate by reaching up to a high shelf or bending down to the floor. It only cares about the raw distance you traveled away from that perfect 30-inch strike zone.
Because both are bad.
Exactly. Reaching up puts strain on the shoulders and upper back. Bending down puts severe strain on the lumbar spine. Both are bad. So both are penalized equally based on the distance of the deviation.
Let's run a scenario to clarify that. Let's say a worker is picking up a tote from a low pallet, and their hands are at 15 inches off the floor.
Okay, so V equals 15. Inside the absolute value brackets, we take 15 minus 30, which gives us negative 15.
Got it.
But the absolute value strips away the negative sign, so it becomes a positive 15.
Right.
We multiply that 15-inch deviation by the tax rate of 0.00075, which gives us 0.1125.
Okay, following you.
Finally, we subtract that penalty from our perfect 1.0, which leaves us with a vertical multiplier of 0.8875, or roughly 0.89.
So picking something up from 15 inches off the floor penalizes you by about 11% of your lifting capacity.
Yeah, and here's the beauty of the absolute value. The penalty is identical if you lift from a high shelf at 45 inches off the floor.
Oh, because 45 minus 30 is also 15?
Yes. Positive 15. The deviation is exactly the same, the tax is exactly the same, and the multiplier is exactly the same at 0.89. The math is just a direct translation of physiological common sense.
That is so cool. So we figured out the penalty for just holding the box in a static pose, but nobody gets hurt just standing perfectly still holding a box.
Rarely.
The injury usually happens when they start to move it. How does the equation account for motion? This brings us to the movement factors, the distance multiplier and the asymmetry multiplier. Let's start with the distance multiplier, the DM.
The distance multiplier measures the vertical travel distance of the object from the origin of the lift to the destination of the lift. We represent this with the variable d.
So it's the actual trip the box takes.
Exactly. If you pick a tote up from a cart that is 30 inches high and you lift it up to a shelf that is 50 inches high, the total vertical travel distance, the d value, is 20 inches.
The formula for the distance multiplier is 0.82 plus 1.8 divided by d. And like everything else, d has physical limits.
Right. The minimum value for d is 10 inches. If a lift travels 10 inches or less, It's considered essentially stationary from a metabolic standpoint, and the multiplier is a perfect 1.0.
And the max.
The maximum value for D is 70 inches, because 70 inches is the functional maximum vertical height an average person can reach from the floor.
Now, if we look at the source data, specifically Table 15-3 from the Bowen EHS materials, I noticed something fascinating about the scaling of this penalty.
What's that?
If D is 10 inches or less, the DM is 1.00. If you move the load 30 inches, the DM drops to 0.88. But if you move it a massive 70 inches, basically from the floor to above your head, the DM only drops to 0.85.
Yeah, it plateaus.
The penalty seems incredibly minor compared to the horizontal multiplier. Why is reaching 20 inches outward destroying 50% of my capacity, but lifting 70 inches vertically barely registers a 15% penalty?
That is an excellent observation, and it highlights a core biomechanical truth. When you lift a load vertically, assuming you are keeping it close to your body, you are primarily utilizing your legs.
Not your back.
Right. You're using the gluteus maximus, the quadriceps, and the hamstrings. These are massive, dense, incredibly powerful muscle groups designed specifically for explosive vertical extension. They can handle the metabolic and structural load of vertical travel with relative ease.
So the engine is big enough for the job.
Exactly. But when you reach horizontally, as we discussed with the lever analogy, you transfer the burden away from the massive leg muscles and place it squarely on the fragile erector spinae muscles and the tiny L5-S1 disc.
Which is a terrible idea.
Terrible. The spine is designed for vertical load bearing and minor flexion. It's not designed to act as a cantilever crane holding weights at arm's length. The equation penalizes the horizontal reach heavily because the biological structures involved are highly vulnerable to catastrophic failure.
That completely clears it up. The math perfectly reflects the anatomy. Okay, let's talk about this second movement multiplier, which is arguably one of the most dangerous movements you can make in an industrial setting. The asymmetry multiplier, or AM.
Oh, this one is critical. Asymmetry refers to a lift that begins or ends outside the mid-sagittal plane.
The mid-sagittal plane. Let's break that down.
The mid-sagittal plane is the imaginary anatomical line that cuts straight down the middle of your body, dividing your face, torso, and pelvis into left and right halves.
Like a mirror.
Yes. If you are lifting an object that is perfectly centered directly in front of your belt buckle, the angle of asymmetry, represented by the variable A, is 0 degrees.
I always liken the asymmetry multiplier to wringing out a wet towel.
That's a very vivid way to put it.
Think about it. Lifting a load straight up and down relies on the structured, stacked alignment of your spinal column. The discs are compressed evenly, like a stack of coins. It's one thing to hold a heavy box. But the moment you plant your feet and start twisting your torso to the side while holding that load, creating an angle of asymmetry, you are geometrically increasing the shear forces on your lower back. You are wringing out the infravertebral discs just like twisting a wet towel.
That analogy is medically spot on. When you introduce torsion, or twisting, under a compressive load, you place immense stress on the annulus fibrosus.
Which is what?
It's the tough, fibrous outer ring of the spinal discs. Twisting under load is the primary biomechanical mechanism for causing that outer ring to tear, allowing the soft inner core to bulge out, which results in a herniated disc.
Ouch!
Yeah, it's brutal. The NIOSH equation recognizes how dangerous this is and penalizes it severely. The formula is AM equals 1 minus 0.00032 times A.
So if a lift is perfectly straight in front of the body, A is 0. 0.0032 times 0 is 0. 1 minus 0 is 1.0. You get a perfect multiplier. You face absolutely no penalty for a symmetric lift.
But let's consult Table 15-4 from our source text to see how rapidly the danger scales. If you have to twist just 45 degrees to pick up a load from a conveyor next to you, your multiplier drops to 0.86.
Just from a small pivot.
Yep. If you have to twist 90 degrees, meaning the load is entirely beside your hip, the multiplier drops to 0.71. You've lost nearly 30% of your lifting capacity just by rotating your torso.
And what's the limit on this one? Because I can't imagine twisting a full 180 degrees without literally breaking something.
You can't. The hard limit is 135 degrees. If the angle of asymmetry exceeds 135 degrees, the multiplier drops to an absolute 0.00.
Wow, another zero limit.
Yes. The equation dictates that nobody should ever be required to twist more than 135 degrees while bearing weight. If an exam question describes a worker twisting 150 degrees to grab a part, the RWL is 0.
Good to know for the test.
From an exam application perspective, and honestly a real-world safety perspective, asymmetric lifting should not just be penalized. It should be engineered out of the process entirely.
But how do you practically do that on a crowded shop floor? I mean, space is tight.
You introduce turntables, you use gravity-fed roller conveyors to bring the product to the front of the worker, or you simply redesign the workstation layout so the worker has enough clearance to move their feet.
Rather than plant their feet and twist their spine.
Exactly. The safety mantra is always, move your feet, not your spine.
Move your feet, not your spine. I like that a lot. All right. We've covered where the lift starts in space, and we've analyzed the mechanics of the movement itself. Now we add the final two real-world variables, the clock and the hands.
Time and grip.
Exactly. How often are you performing this task, and how hard is it to physically hold on to the object? Let's dive into the frequency multiplier, or FM.
The frequency multiplier is a bit of a departure from the others because there isn't a simple algebraic formula for you to calculate on the fly. You can't just plug a number into your calculator.
No absolute values this time.
Nope. Instead, you have to determine the multiplier using a comprehensive matrix, which is table 15-5 in the source materials. The FM is based on the interaction of three distinct variables.
Okay, what are they?
First, the frequency rate of lifts per minute. Second, the total duration of the lifting task over the shift. And third, the vertical height of the lift from the floor.
Why does this one require a matrix? Why is it so complicated compared to the others?
Because we were shifting from biomechanical stress to metabolic and cardiovascular fatigue.
Oh, I see.
Lifting a 20-pound box once an hour is an isolated biomechanical event, but lifting that same 20-pound box 10 times a minute for an entire 8-hour shift is a severe cardiovascular event.
It's a workout.
A grueling one. As the body fatigues, lactic acid builds up, oxygen depletion occurs, and the core stabilizing muscles of the abdomen and back lose their ability to support the spine.
And when the muscles fail?
When the muscles fail, the stress transfers directly to the ligaments and discs, and injury risk skyrockets.
Okay, let's break down those three variables in the matrix. First, we have frequency, measured in lifts per minute. This can range from less than 0.2 lifts per minute, which translates to roughly 1 lift every 5 minutes, all the way up to a frantic 15 lifts per minute.
Yes. And second, we have work duration, which is classified into 3 categories. Short duration is 1 hour or less, moderate duration is 1 to 2 hours, and long duration is 2 to 8 hours.
And the third variable in the table is the vertical height of the lift, V. The matrix gives different multipliers depending on whether V is less than 30 inches, meaning below the strike zone, or greater than or equal to 30 inches.
That's right.
Why does the height matter for frequency, though?
Energy expenditure. Lifting a box from the floor requires you to lower and raise your entire body weight in addition to the load. You're basically doing a full squat.
Oh, yeah. That makes sense.
That burns exponentially more caloric energy and oxygen than simply shifting a box from a waist-high table to another table.
Let's pull a practical example directly from the SPAN CSP Volume 1 source material to show how this matrix works in practice. There's a problem, question 46, that asks for the RWL of a task where the frequency of lift is once every 5 minutes for an 8-hour shift.
Okay, let's trace that through the matrix. Once every 5 minutes equates to a frequency of 0.2 lifts per minute.
And an 8-hour shift puts us firmly in the long duration category.
Yes. If we look at the table for a frequency of 0.2 and a duration of more than 2 hours up to 8 hours, the frequency multiplier is 0.85, assuming the lift is below 30 inches.
Think about that. Even at a very slow pace, just 1 lift every 5 minutes, you still lose 15% of your lifting capacity just for the metabolic fatigue accumulated over a full workday.
And as the frequency increases, the penalty becomes brutal. If a worker on an assembly line is doing 10 lifts per minute for an 8-hour shift, your multiplier plummets to 0.26.
Wow, 0.26.
You are retaining only a quarter of your baseline lifting capacity. The 51-pound limit drops down to roughly 13 pounds. The math just screams that highly repetitive motion over long periods is devastating to human tissue.
That is eye-opening. And that leads us directly to the final variable, the coupling multiplier, or CM.
Right.
Coupling is simply the ergonomic term for the interface between the worker's hands and the object. Are you holding a custom-molded, rubberized handle, or are you trying to pinch the slick edges of an oversized cardboard box that's falling apart?
The source material categorizes coupling into 3 distinct classifications: good, fair, and poor. Good coupling means the object has an optimal design. This includes things like well-designed cutout handles on a sturdy box or a comfortable, rigid, cylindrical grip on a tote.
And poor coupling.
Poor coupling involves containers with less than optimal design. Think of bulky objects with no handles. loose parts that shift unpredictably, or non-rigid bags that sag in the middle, like trying to lift a 50-pound bag of wet sand off the floor.
Oh man, wet sand is the worst. And just like the frequency multiplier, you use a table 15.7 to find the actual value.
Right.
But I have to bring this up because it's such an interesting quirk in the data.
Oh, the fair grip anomaly.
Yes, I noticed an anomaly when I was studying this table. If you have a good grip, your multiplier is a perfect 1.0, regardless of the height. If you have a poor grip, your multiplier is 0.90, regardless of height.
Right.
But the fair grip has a split personality. If your vertical height is below 30 inches, a fair grip gives you a multiplier of 0.95. But if your vertical height is at or above 30 inches, that fair grip multiplier suddenly jumps back up to a perfect 1.0.
It does seem contradictory at first glance. Why would a mediocre grip suddenly become unpenalized just because you were lifting higher up?
Yeah, explain that to me. I'm having trouble visualizing why the height changes the grip strength required.
The physiological mechanism behind this has to do with the interaction of gravity, biomechanical leverage, and the maximum grasp forces required by the flexor muscles in the forearms.
Break that down for me.
Think about the mechanics of lifting a heavy box from the floor. When you reach down below your waist, your arms are hanging straight down.
Okay, picture that.
The entire 50-pound weight of the object is pulling directly against gravity, and the only thing keeping it from hitting the floor is the pinch strength of your fingers.
That's a lot of strain on the fingers.
A fair grip, like a shallow finger hold or a thin cardboard flap, is much more likely to slip under that direct vertical tension. When you feel it slipping, your natural reflex is to squeeze harder.
Which hurts.
It introduces intense muscular fatigue to the forearms and forces you to make jerky, unstable compensations with your spine to catch the load.
Ah, I see. The weight is literally hanging from your fingers. But when you lift an object at or above waist height, your biomechanics completely shift.
Exactly.
You aren't hanging it from your fingers anymore. You are usually bending your elbows, getting underneath the object, and cradling it against your torso. The burden shifts from your fragile forearm flexors to your massive biceps and chest muscles.
You've got it perfectly.
Yeah.
At higher elevations, you don't need a perfect handle to maintain control because you are supporting the object's center of gravity from below rather than hanging it from above.
So the grip matters way less.
Exactly. Therefore, the NIOSH data determined that a fair grip is entirely sufficient at those heights and doesn't warrant an extra biomechanical penalty. The math is incredibly nuanced.
That makes perfect sense when you visualize the actual work on the floor. Now, before we move on to using all these multipliers in a real scenario, I want to talk about exam strategy.
Always a good idea.
I was digging through the BCSP, CSP preparation questions last night, and I got totally tricked by one of them.
Oh, let's hear it.
Question number 116 gives you this massive paragraph of data. It says the load constant is 51, the horizontal multiplier is 0.75, the vertical is 0.90, the distance is 0.87, the asymmetric is 0.85, the frequency is 0.45, the coupling is 0.95, and then it throws in an environmental multiplier of 0.88.
And let me guess, you dutifully multiplied all of them together.
I absolutely did. I hammered them all into the calculator, got a tiny weight limit, picked the answer, and got it dead wrong.
Yep.
The solution the book specifically noted, there is no such parameter as an environmental multiplier. They completely fabricated a variable just to bait me.
That is a classic, brutal exam strategy. Test writers know that under time pressure, candidates will just take all the numbers presented and multiply them together. They will invent convincing-sounding terms like transitional multiplier, environmental multiplier, or thermal coefficient, and assign them realistic decimal values like 0.80.
It's so mean.
You must be disciplined. You must stick rigidly to the core 6 multipliers: horizontal, vertical, distance, asymmetry, frequency, coupling, HM, VM, DM, AM, FM, pan, CM. If you see phantom data, cross it out immediately. Do not let them bait you.
That is such a vital warning. So we've survived the gauntlet of the formula. We have all 6 multipliers. We've carefully multiplied them against our baseline of 51 pounds, and we have successfully calculated our recommended weight limit.
The RWL.
Let's say our RWL comes out to 25 pounds. We know what the healthy limit is, but knowing the limit is only half the battle. As a safety professional, we have to compare that theoretical limit to the grim reality of what the worker is actually doing.
Right.
So what does this all mean? How do we measure the danger?
We use the lifting index. The recommended weight limit tells you what should be lifted. The lifting index, or LI, tells you how bad the actual lift is. The NIOSH manual defines the lifting index as a relative estimate of the level of physical stress associated with a particular manual lifting task.
The formula for the lifting index is incredibly straightforward. It is simply the actual object weight divided by the calculated RWL.
Very simple division.
So if your calculated RWL is 25 pounds, but the worker is actually manhandling a 50-pound box, your lifting index is 50 divided by 25, which gives you an LI of 2.0.
And our goal always is to engineer the job so the lifting index is 1.0 or less.
Because an LI of exactly 1.0 means the actual weight perfectly matches the recommended weight limit.
Exactly. An LI less than 1.0 means the task is actually safer than the baseline limit. But an LI greater than 1.0 mathematically proves that the task poses an increased risk for lower back pain and injury for a portion of the workforce.
I understand the formula, but let's make it real. What does an LI of 2.0 or 3.0 actually look like on a shop floor? How do we use this to diagnose and fix a broken process?
To explore this, let's walk through a detailed practical case study straight from the NIOSH application manual.
Yeah.
We're going to evaluate the punch press operator.
Awesome, let's do it.
This is a fantastic case study because it illustrates how complex real-world operations are and how the equation acts as a diagnostic tool. Let's set the scene. You are walking through a noisy machine shop. A typical operation involves a punch press operator handling small, lightweight metal parts all day.
Okay, sounds fine so far.
The daily work is fine. However, occasionally, specifically once per shift, the operator must reload the machine. They have to muscle a heavy reel of supply stock from the floor, lift it up, and thread it onto the machine's spindle.
We have our variables from observing the worker. The reel of supply stock weighs exactly 44 pounds. The diameter of the reel is 30 inches, and the worker has to hold it awkwardly by the edges, meaning their hands are spread 12 inches apart.
And crucially, the source text notes that significant control of the load is required at the destination of the lift, owing to the design of the machine.
Because you can't just throw the reel in the general direction of the press. You have to carefully align the center hole of the heavy reel onto a steel spindle.
That note about significant control is the trigger for a major procedural rule in the ASP equation. Because the worker has to carefully aim and control the load at the end of the movement, we cannot just calculate the RWL once.
We have to do it twice.
We have to calculate the entire RWL formula twice. Once for the origin of the lift when they pick the heavy reel off the floor, and once for the destination of the lift when they precisely align it onto the spindle. We need to find out which part of the movement is the bottleneck, causing the most biomechanical stress.
Okay, let's look at the origin data first. When the worker bends down to pick up the reel from the floor, they have to reach forward slightly because the reel is large and they don't want it banging against their shins. We measure from their ankles to their hands, and the horizontal distance, H, is 23 inches.
And they are lifting from the floor, but their hands are gripping the sides of the reel, which puts their hands at 15 inches off the ground. So V is 15.
Now, for the destination data, they're lifting the reel up and leaning into the machine to thread the spindle. The horizontal distance remains exactly the same. H is still 23 inches.
But the vertical destination height is way up near their chest. It's 63 inches off the ground. So V destination is 63.
Let's run the math for the origin point where they pick it up. We start with our perfect load constant of 51 pounds.
Right.
Our horizontal multiplier for H equals 23 is 10 divided by 23, which is 0.44.
Brutal penalty right there.
Yeah. Our vertical multiplier for V equals 15 is calculated using the absolute value of 15 minus the 30-inch strike zone, which gives us a 15-inch deviation. We multiply that by 0.00075 and subtract from 1, resulting in a multiplier of 0.89.
Now, the vertical travel distance, D, is the difference between the destination height of 63 inches and the origin height of 15 inches. 63 minus 15 is 48 inches of travel. Using our formula for distance, we get a distance multiplier of 0.86.
Okay, moving down the line.
The worker is standing square to the load, assuming no twisting, so the asymmetry multiplier is a perfect 1.0. The frequency is very low, only once per shift, so the frequency multiplier is a perfect 1.0.
And because the reel is large, awkward, and lacks a real handle at knee level, the grip is classified as fair.
Yes, and since the lift is below 30 inches, that fair grip yields a coupling multiplier of 0.95.
So when you multiply all of those fractions together, 51 times 0.44 times 0.89 times 0.86 times 1.0 times 1.0 times 0.95, you get a recommended weight limit for the origin of the lift of approximately 16.3 pounds.
Now remember, the actual physical weight of the reel is 44 pounds. To find the lifting index at the origin, we divide the actual weight by the calculated limit. 44 divided by 16.3 gives us a lifting index of 2.7.
That is massive, a lifting index of 2.7. That means the simple act of picking this reel off the floor is almost 3 times the recommended stress level for a human spine.
It is. But wait, we still have to calculate the stress of placing it on the spindle at the destination.
Okay, let's run those numbers. At the destination, the horizontal reach is still 23 inches, so the HM is still a brutal 0.44.
But the vertical height is now 63 inches. Reaching that high is 33 inches outside the 30-inch strike zone. The absolute value math drops the vertical multiplier significantly to 0.75.
The distance, asymmetry, and frequency multipliers remain identical to the origin calculation.
However, remember our quirky rule about coupling. Because the lift is now above 30 inches, the worker is cradling the reel from the bottom. That fair grip is no longer penalized, so the coupling multiplier jumps up to a perfect 1.0.
So for the destination RWL, we multiply 51 times 0.44 times 0.75 times 0.86 times 1.0 times 1.0 times 1.0. That gives us a recommended weight limit of approximately 14.4 pounds.
Again, we calculate the lifting index. The actual weight is 44 pounds. We divide 44 by the new RWL of 14.4 pounds, which gives us a lifting index at the destination of 3.0.
Let's stop and look at the whole picture. The origin LI is 2.7. The destination LI is 3.0. If we connect this to the bigger picture, what does a lifting index of 3.0 actually mean for the safety professional evaluating this workstation? What are we supposed to do with this number?
If we connect this to the bigger picture, it means you have a massive, glaring red flag on your shop floor. According to NIOSH, any task with a lifting index greater than 1.0 poses a risk to some workers. But a lifting index greater than 3.0 indicates a highly stressful task that puts nearly all workers at an imminent risk of severe musculoskeletal injury.
That's unacceptable.
It demands urgent, immediate engineering interventions. You cannot rely on administrative controls like lifting training or team lifting for an LI of 3.0. You must re-engineer the physics of the job.
And the beauty of the equation is that it doesn't just tell you that the task is dangerous, it literally gives you the blueprint for how to fix it. You just look at the multipliers that are dragging the score down.
Exactly. Look closely at the horizontal multiplier. At 23 inches, the multiplier is 0.44. The worker is losing more than half their lifting capacity just because the machine design forces them to stand nearly 2 feet away from the spindle.
Right.
If you could engineer a way for the worker to get closer to the reel, perhaps by removing an obsolete guardrail, notching out the table, or changing the orientation of the machine so that the H value becomes the minimum 10 inches instead of 23.
The HM becomes 1.0.
Yes. You would instantly more than double the safe lifting capacity without changing the weight of the object.
Or look at the origin height. The vertical multiplier is punishing them for picking it up off the floor. What if we mandate that supply stock can never be stored on the floor? What if we implement a spring-loaded scissor lift table that keeps the reel in exactly 30 inches?
The vertical multiplier becomes a perfect 1.0. The math acts as a diagnostic X-ray for the workstation.
That is the true power of the NIOSH equation. It turns safety professionals into biomechanical detectives. You isolate the variables, you identify the bottleneck, and you target your capital expenditure exactly where it will have the maximum mathematical impact on reducing risk.
It's an incredibly powerful multi-tool.
It really is. But as a safety professional, and especially as an ASP candidate facing tricky, scenario-based, multiple-choice questions, you also need to know its blind spots.
Oh, absolutely.
When does this multi-tool become useless? Because no single formula can account for every bizarre thing that happens in a manufacturing plant. Let's talk about the rule breakers. When should you absolutely not use the NIOSH equation?
This is critical for both the exam and field practice. The revised NIOSH equation is highly specific. It was designed under very controlled, laboratory-derived assumptions. If your real-world task violates those assumptions, the equation becomes invalid.
It'll just spit out garbage data.
It will produce numbers, but those numbers will be mathematically meaningless. First and foremost, it applies only to two-handed lifting. It assumes you are using both hands symmetrically to lift the object.
So if a worker is using one hand to yank a heavy bag off a conveyor belt, or carrying a heavy bucket in one hand, the equation is out the window.
Correct. The biomechanics of unilateral loading, putting all the stress on one side of the spine, are completely different. Furthermore, it assumes the lifting motion is smooth and controlled.
So no throwing.
Right. It does not apply to high-speed lifting, sudden jerky movements, or throwing objects. It also does not apply to lifting from seated or kneeling positions, because that alters the entire pelvic structure and eliminates the leg muscles from the equation.
What about the physical environment? I imagine you can't use this if someone is crammed into a tiny space.
Exactly. It assumes the worker is standing on their feet with unrestricted movement. If they are in a cramped, restricted workspace, like a mechanic working inside a compact engine bay or a miner in a low-clearance tunnel where they cannot adopt a natural posture, the mathematical assumptions fall apart.
The source text also highlights the object itself and the climate. You cannot use this equation if the object is highly unstable, like carrying a sloshing bucket of liquid that shifts the center of gravity dynamically, or an aggressive, squirming animal in a veterinary clinic.
Good luck applying math to a squirming dog.
Exactly. And it absolutely cannot be used if the environment is extreme. If the temperature or humidity is highly elevated, or if the floor is slippery, the equation is void.
I want to expand on the temperature aspect because it ties back to physiology. Why does extreme heat invalidate a biomechanical lifting equation?
Because they're sweating.
Well, yes, but internally, because in extreme heat, the body undergoes vasodilation to cool itself. It shunts blood away from the core muscles and toward the skin. This severely reduces the metabolic efficiency and endurance of the muscles supporting the spine. The 51-pound load constant assumes a thermoneutral environment. Heat destroys that baseline.
That makes total sense. Furthermore, and this is a major distinction for the exam, the equation is exclusively for lifting and lowering. It is not designed to evaluate carrying, pushing, or pulling.
Right.
Nor does it apply to lifting using wheelbarrows or long-handled shovels. The leverage, the momentum, and the mechanics of a shovel are completely alien to a standard vertical manual lift.
This is exactly where the ASP exam writers will try to ambush you. I can picture the question stem right now. You get a massive paragraph. It reads, a worker is operating in a humid 100-degree trench. They were using a long-handled shovel to lift 20 pounds of wet clay from a depth of 15 inches, twisting 45 degrees, and throwing it into a wheelbarrow over an 8-hour shift. Calculate the RWL.
And they will give you every single variable perfectly laid out to tempt you into doing the math.
Every single one.
And if you fall for it, you will spend 5 precious minutes furiously punching absolute values and fractions into your calculator, only to confidently pick the wrong answer.
Yep.
The correct answer in that scenario is not a number. The correct answer is a conceptual understanding that the NIOSH equation is completely invalid for that scenario. It violates almost every rule. It uses a shovel, it's a throwing motion, it's in a restricted trench, and it's in a 100-degree environment.
It's the ultimate trap. You have to know when to leave the tool in the toolbox.
But wait, if the NIOSH equation is invalid for all these other common tasks, like pushing a heavy cart, carrying boxes across a warehouse, or shoveling, how are we supposed to evaluate them? We can't just ignore them.
We don't ignore them, but we change our scientific methodology. The source material specifies that if non-lifting activities like holding, pushing, pulling, carrying, walking, and climbing account for more than approximately 10% of the total worker activity during the shift, the biomechanical assumptions of the NIOSH equation are no longer sufficient to assess risk.
So what do we use?
In those cases, measures of workers' energy expenditure and heart rate must be used to assess the metabolic demands of the tasks. You shift away from biomechanical engineering formulas and move toward physiological monitoring.
Which is an entirely different domain of occupational health, but just as vital to protecting the worker. You just have to make sure you're using the right scientific tool for the specific job.
Absolutely. The NIOSH equation is a scalpel. It is incredibly precise for what it does, but you shouldn't use a scalpel to chop down a tree.
Well, we have covered an immense amount of ground today. We have successfully conquered the core concepts of ASP Domain 1, Topic 9. We started with the murky, subjective complaint of a sore back and unpacked the rigorous 3-discipline history of the revised NIOSH Lifting Equation.
We covered a lot.
We established the golden baseline, the load constant of 51 pounds. We survived the gauntlet of the 6 multipliers, deeply analyzing the anatomy and physics of how horizontal reach destroys the L5-S1 disc, how vertical height interacts with the strike zone, how travel distance and asymmetric twisting act like wringing out a wet towel on your spine.
And how metabolic frequency and hand coupling all mathematically degrade a worker's safe lifting capacity.
And most importantly, we didn't just learn the formulas, we applied the math. We calculated the recommended weight limit, and we used the lifting index to diagnose a dangerously overloaded punch press workstation.
We proved that an LI of 3.0 requires immediate engineering interventions, and we showed how the multipliers themselves highlight exactly where to spend your engineering budget.
We also identified the exam traps. We know to watch out for fake transitional multipliers designed to bait us, and we know exactly when the equation is a rule breaker like with shoveling, extreme heat, or one-handed lifts, and shouldn't be used at all.
For those of you listening who are deep in preparation for the ASP exam, I want to leave you with a word of direct encouragement. I know that looking at a massive formula with 7 variables, absolute values, and complex matrices can feel completely overwhelming.
For a lot of math.
But as we've discussed today, this isn't just arbitrary academic math. It is a deeply logical, predictable story about how the human body interacts with gravity and space. Once you understand the why behind the penalties, why reaching out levers the spine, why twisting shears the discs, why raising your hands changes your grip strength, the math simply becomes a translation of common sense.
I couldn't agree more.
You don't have to memorize a random string of numbers. You just have to understand the mechanics of the human machine. You can absolutely master this.
That is perfectly said. The math is just telling the anatomical story of the human body. Before we wrap up, I want to leave you with one final provocative thought to ponder as you look at your study materials tonight. The entire NIOSH equation, as brilliant and complex as it is, revolves entirely around that golden load constant of 51 pounds. And that 51 pounds assumes a baseline of a healthy worker.
Right. It is statistically designed to protect 75% of the healthy female population and 99% of the healthy male population.
Exactly. But look at the modern industrial landscape we are actually operating in. Our workforce is rapidly aging. We have millions of workers who are performing duties with pre-existing injuries, microtraumas, arthritis, or chronic conditions where they simply no longer fit the demographic definition of a healthy worker.
That's very true.
So the question is, how might the safety profession and tools like the NIOSH equation need to adapt in the coming decades? If that baseline of 51 pounds no longer applies to the physical reality of the people walking onto the factory floor every morning, how will we calculate safety in the future?
That is the true frontier of ergonomics right there. It forces us to ask if a universal standard is even possible anymore, or if we need to leverage technology to individualize the math for every single worker.
It's a huge question, and one you'll undoubtedly face in your career long after the stress of the ASP exam is over. Thank you so much for joining us for this QHSE Talks. Keep studying, trust your preparation, trust the science, and as always, stay safe out there.